Alright, in this video we're going to be doing some polar area practice for CalBC. And so we're going to start with this one. Looks like a crescent moon. And they gave us the bounds of integration, okay, so that's really helpful. And that happens quite a bit, right? So we know that we're going to be integrating from pi over 3 to 5 pi over 3. Okay. And then if I draw a kind of a radial line from the origin to the edge of the region that I'm trying to find the area of, I hit both curves. So that's where I know I'm going to have to run the integral of 1/2 r squared for one of them and 1/2 r squared for the other one and subtract. I can do that inside the same integral. I just have to subtract the squares, right? Not subtract and then square. Anyway, so I'm going to say, all right, this area is, we know that it's 1/2 r squared d theta. So I'm going to say half of the integral from pi over 3 to 5 pi over 3 of the outside r is r equals 4. And then the inside r is 3 plus 2 cosine theta. Okay, 1/2 r squared. Okay, now we know that we can combine these two into this integral that I'm going to type into the calculator, right? So there's less typing. So it's going to be 1/2 of the integral from pi over 3 to 5 pi over 3 of 16 is 4 squared minus this thing squared, 3 plus 2 cosine theta. Okay, close that off, square it. With respect to x, we can get 21.730. Should probably pull up my work from 2 years ago and see what I got. I, of course, did not run these through the calculator. Okay, but you know, it looks almost exactly like what I just wrote there, so that's a good sign. Okay. The figure shows the graphs of r equals f of theta and r equals g of theta, where f of theta is 1 plus sine theta cosine 2 theta. I gotta think that's the inside curve, okay, because we know what 2 cosine theta looks like. It's a circle centered, or not centered at the origin, but butting up against the origin along the x-axis. Okay, so this is going to be g, and then this one's going to be f. Okay. And find the areas of regions R and S. All right. Well, we can find the area of region R just by integrating on F. And so I'm going to start with that, and then probably the area of region S, I'm going to be able to just subtract, take the whole circle and subtract the area of region R. So, area of R, we know it's 1/2 of the integral of R squared. Okay, radius squared, not region R. So this is f of theta squared. And we're going to integrate from 0 to pi over 2. Because it told us. Okay, so I'm going to say, all right. You know, I don't think I'm going to need that curve again, so I'm not going to put it in white or anything. So I'm going to do half of the integral from 0 to pi over 2 of f of theta squared. So 1 plus sine theta cosine 2 theta squared d theta. Okay. I get 0.648. Okay. And now, if you wanted to find the area of S, wait, that's a circle, it's got radius 1, so the whole thing would have area pi times 1 squared would be pi. So the half circle is pi over 2 units of area, and pi over 2 minus that will be the area of S. you can do that. But if you wanted to practice your writing of this as an integral, then we would start from the origin, go out radially to the edge of S, and we see we hit both curves, so I know I'm going to need to subtract. Okay. So area of S would be 1/2 of the integral still from 0 to pi over 2, but it would be outside is g of theta squared minus inside would be f of theta squared d theta. Okay. And then I could say, well, bless you, I'd run this in here, probably insert a minus. Okay, and then what is g of theta squared? 2 cosine theta, so 2 cosine theta squared. Okay, minus, yeah, that looks right. Yeah, and I get 0.922. But I could also do pi divided by 2 minus this number, and it will do division before the subtraction, like PEMDAS, right? And I get the same number, right? So how do you want it? So it's 0.922. Right. Let R be the region that's inside the graph of R equals 3 and outside the graph of what? Inside? Okay, so evidently this is not the shaded region. Hold on a second. Yeah, and then I lost my pen. It definitely is not the shaded area, although maybe I'll do the shaded area as well, because this is it's like a free response question from not that long ago. But inside R equals 3, that's inside the circle and outside the lumpy thing. Okay, so that's going to be here. I'll call it area A. Okay. So area A is going to be, if I draw the radial line to the edge of the region, I'm hitting 2 curves, which means that I'm going to be subtracting, and that's in the best variety yet, but I'll have that the other thing happening when I find the area of the shaded region. So area A will be equal to 1/2 R squared, but R squared minus the other R squared. So the outside one is 3. The inside one is 3 minus 2 sine 2 theta. And we're going to go from 0 to pi over 2. Okay, this one didn't give you any bounds, but it was just kind of self-evident. The first quadrant, that's 0 to pi over 2. Okay, when I go to find the area of the shaded region, I'm going to need to go start at 0 and eventually end up at pi, but it's going to require 2 integrals. But you might already know that. Okay, so this is going to be something I need to use a calculator for, right? Because we don't do sine squared by hand, even though we probably could. Let's say half of the integral from 0 to pi divided by 2, which I didn't write in there, but let's do that. Okay, integral from 0 to pi over 2 of 9 minus 3 minus 2 sine 2 theta squared d theta. You get 4.429. All right, the area of region R, the shaded region, well, if I go from, if I go from the origin to the edge of R at any time, I'm only ever hitting one curve. But after pi over 2, the curve that I'm hitting switches, right? So I know I'm going to have to add together 2 different integrals. So I'm going to say that the area of region R is going to be equal to 1/2 of the integral from 0 to pi over 2 of just this thing. Right, because I'm just going to this curve here. 3 minus 2 sine 2 theta squared d theta plus the integral from pi over 2 to pi on this one. Now, if you know that's a quarter circle with radius 3, you could say that's 9 pi over 4. Okay, but I'm really focused on the integrals today, so I'm just going to do everything with an integral. So half of integral from pi over 2 to pi, right? That's pi over 2. This is pi. Of r squared is 9 d theta. Okay. Now, I can probably save myself some typing by just clearing out the 9 minus and getting that, and then adding to it the integral from pi over 2 up to pi of r squared is 9 dx d theta. And then you'll get 16.777. Okay, but I could also do this and add 9 pi divided by 4 and get, why would that happen? Pi over 2 to pi. Ah, what did I forget? It's not the same. It's the 1/2, right? So I'm going to go in here, and I'm going to clear out this one. Can I do that? Yeah, I'm going to do that and say plus half the integral from pi over 2 to pi of 9 d theta. And then I'll get that 9.708 number. Okay. I'm glad I caught that. And yeah, and then again, if I was to grab this number and add 9 pi divided by 4, then I'll get the same thing. Okay, whew, that was bad. Okay, let's make that same error again. Okay, that was number 3. Okay, find the area of the shaded region. All right, great. Okay. Sometimes you can use symmetry to do, to not integrate all the way, but I don't exactly like this one. I mean, it's symmetric across the y-axis, but then I'd have to, I'd have to split this up into too much stuff. And so what I think I'm going to do is, so the 4 minus 2 sine theta, it's not a very good drawing of it. It's definitely not just like completely constant across that way. That's not how that curve works, but what we're going to do, if we go from, again, if we start from the origin and draw a radial line to the edge of the shaded region, we're never hitting 2 curves, right? We're only ever hitting 1 curve. It's just which curve we're hitting has traded off. So what I'm going to do is I'm going to find, okay, they told me that that's pi over 6, and this is 5 pi over 6. And if you want to, think real hard about it and find like kind of a faster way to do it, you can be my guest, but I'm going to do this like the slowest and safest way, which would be to start at 0 and go all the way over to 2 pi. So I'm going to start at 0 and I'm going to go up to pi over 6. Okay, and that would be, r squared would be 9. Plus, then I'm going to go from pi over 6 to 5 pi over 6 on the other curve. 1/2 r squared 4 minus 2 sine theta squared d theta. And then the third piece is going to be from 5 pi over 6 all the way over to 2 pi. And yeah, you could definitely figure out, what portion of a circle that was, and then what portion of the circle this was, and do these two together in one without an integral, or you could put them together. And there's all sorts of ways you could do this with fewer integrals. But I know that this is going to work, and I feel like this would be the thing you would first thing to do when you were first learning how to take polar areas, which is exactly where you are. So. Okay, plus 1/2 of the integral from pi divided by 6 up to 5 pi divided by 6. R squared would be 4 minus 2 sine x dx plus out to 2 pi of r squared is 9. And then we get 24.709. Find the area in the second quadrant enclosed by the coordinate axes in the graph of 3 theta plus sine theta. Okay, I think, pretty sure that this is just going to be the integral from pi over 2 to pi of this thing squared. But just to make sure that nothing weird is happening, I am going to sketch the graph of this in polar mode. So that would be 3 theta plus sine theta. Yeah, I don't really see this going. It's just zoom standard. Yeah. Nothing weird is happening here, so I can just go from pi over 2 to pi. Okay, I accidentally touched the screen with my pen. That was a mistake. So, yeah, so I'm going to switch my mode back. And I'll have 1/2 r squared, and this is from pi over 2 to pi, because it said second quadrant, of r squared is 3 theta plus sine theta squared d theta. You get 47.513. Right, but that's not ever enough, right? You see that much area, that's not going to be the appropriate thing to give. Right, I'm going to say, all right, it looked kind of like that. I mean, that's really an oversimplification, but, it's good enough. And I'm going to say I'm integrating 1/2 of the integral from pi over 2 to pi of r squared d theta, and that gives me that. All right, area of region S. This one is a little tricky. It's like, what are the theta bounds? It doesn't tell me, so you're going to have to do a little bit of work to find them. So we go back over here to polar. Let's look at 1 minus 2 cosine theta. Okay, our window is 0 to 2 pi, so I should be able to figure this out, right? Okay, we're going to graph it, and that's interesting. All right. Maybe I'll have it just go from 0 to 1 pi. All right, yeah, and then that looks exactly like what I'm seeing, except maybe I could zoom in. Yeah, and then I can still see the place I need. So I'm going to trace, and that's where theta equals 0 on that. Okay, and then I'm going to go right to 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 8 clicks took me back to the origin. That's pi over 3. Okay. So it would be 1/2 of the integral from theta equals 0 to theta equals pi over 3 of r squared d theta. Okay, so I'm going to go back into function mode, and I'm going to say 1/2 of the integral from 0 to pi divided by 3. 1 minus 2 cosine theta squared d theta, 0.272. Right. All right, this one is exactly like that one I did earlier that had it at the top. It's all right. I mean, it doesn't look meaningfully different at all, but oh well. Okay, I'm going to split this up. I'm going to go from 0 to this intersection point, which they said was 2 pi over 3. And I'm going to be integrating from 0 to 2 pi over 3 on r equals 2. So 1/2 of the integral from 0 to 2 pi over 3 of r squared d theta plus 1/2 of the integral from now 2 pi over 3 to 4 pi over 3. R squared is this thing squared. Plus, okay, the third one would just be from 4 pi over 3 to 2 pi of r squared d theta. And just like the other one, I'm sure that there's a faster way to do this, but I'm just doing this, I think, the clearest and most obvious way for when you're starting out. 4d theta plus 5 times the unequal from let's do both of those and then add 1/2 of pi over 3 to 2 pi of r squared. And I get 10.370. Right, now, I was thinking, like, is this even reasonable? Is this a reasonable amount of area? Because I was like, does that even look like 10? But if you think about it, this is a circle with radius 2, the whole circle that I've cut some out of. And a circle with radius 2 would have area of 4 pi, right? Pi r squared. And 4 pi is even bigger than 12, so this seems kind of reasonable to me. Okay, find the area of the region bounded by the curve on the x-axis. We can do that. That's going to be, okay, this is just 0 to pi, right? R squared d theta. Okay. Let's see. Four, 3, 8, 2. Okay. This one's a little tricky. Okay, this one, again, if you start and draw the radial line, you're only ever going to get hit one line, so you know you're going to have to do the thing where we're going to hand off from one curve to the other at the intersection point. Okay, we're going to need to find this actual intersection, although it does look like, I think it's 1, 1. But the whole world of polar intersections is definitely a world we don't want to go into. Let's see, r equals square root 2. Yeah, that would contain the point 1, 1. If you think about what would happen at pi over 4 with the unit circle if it was scaled up by the square root of 2. And so, yeah, I think that's just going to do it for us. Both of these points are going to be pi over 4. Okay? So what I'm going to do, I'm going to actually zoom in, and I haven't done this in this video. So up until pi over 4, we're going to be adding on, let's get this pen started. We're starting at theta equals 0, right? And we're just going to keep adding areas this way, right, as we're rotating. Adding up these pieces of pizza. And then we get to here, okay, and then it changes. Okay, that amount of area that I have just, accumulated is going to be 1/2 of the integral from 0 up to pi over 4, and that's on the circle centered at the origin, which is r equals square root of 2, and so I'm going to square that, and I'll get 2. And then after that, I'm going to start adding onto this curve. And it's hard to see because it's really not adding very much, especially by the time we're over here. But that's going to be 1/2 of the integral from 0. No, not 0. So we handed off at pi over 4, so I'm going to pick back up at pi over 4. integral from pi over 4 to pi over 2. Now the fact that this happens at pi over 2, well, I think the best way to see it would be, this is the graph of r equals 2 cosine theta, and think about a value of theta that would make r equals 0. It's pretty much just pi over 2 and 3 pi over 2, so it's not, doesn't seem reason to believe it would be 3 pi over 2, so I'm just going to say it's pi over 2. Also, these r equals 2 cosine theta circles, I told you last time that those trace out their graph on 0 to pi, so that's another reason to believe me on that. All right, so we take 2 cosine theta and we square that. Okay. And we're going to add these together. And in total, we're going to get, let's see. Well, I guess I can zoom out. Couldn't see that, but you know, do all that. 1.071. All right, and I've still got 3 of problems. My class is about to start back up, so I think I'm just gonna call it for this video and do the rest of these in a separate video. But this is a good set of practice problems for us. Thanks for watching.